On November 23, 2023, the LIGO Observatory detected a faint echo from halfway across the cosmos, a space-time ripple originating 7 billion light-years away. The collision that caused it was almost incomprehensibly violent. In a fraction of a second, it released 15 solar masses of energy. That is more energy than every single star in the entire universe produced combined at that exact moment. This specific event perfectly matched a century-old prediction made by physicist Albert Einstein that when something unimaginably heavy accelerates through space, it generates gravitational waves that stretch and squeeze the very fabric of the universe itself. To capture those waves, scientists rely on facilities like LIGO, which fires lasers down miles of concrete vacuum pipes to measure space-time fluctuations smaller than 1,000th of a proton. But when the team analyzed the data from GW 231123, they found a signal that looked different from every previous detection.
Instead of confirming our models, the data pointed to two objects that refused to align with the known laws of physics.
According to our current models of the universe, neither of these black holes should exist. The loudest signal humanity has ever captured came from objects that contradict our current rules for how stars live and die.
The two black holes in this unusual collision weighed 103 and 137 times the mass of our Sun. Additionally, both objects were spinning at nearly the speed of light. Black holes are incredibly extreme, but they are surprisingly simple to categorize. We define them by only 3 traits: mass, spin, and electric charge. When you plug the numbers from GW 231123 into our current models, the math fails. In our established understanding of the universe, black holes with this specific combination of mass and spin are theoretically impossible. To understand why, we have to look at how these objects are usually born. Typically, when a massive star, say 20 to 30 times the size of our Sun, runs out of fuel, its core collapses inward under its own gravity to form a standard black hole. But things change with ancient giant stars that hold between 130 and 250 solar masses. Many of these monsters end their lives in violent supernovae that tear the star apart completely, leaving absolutely nothing behind. Other giant stars go through a pulsating phase, violently throwing off layer after layer of material until only a tiny neutron star or a very small black hole remains. This diagram maps out black hole sizes, and it illustrates a massive problem. Because giant stars destroy themselves or shed their mass, there is a dead zone between 50 and 130 solar masses where star-born black holes cannot exist. Physicists call this the mass gap. Yet the objects that collided to create our signal were 103 and 137 solar masses. Both fall squarely inside this forbidden zone. If a star couldn't create a black hole this heavy, scientists initially hypothesized that they must have grown this large over time by eating smaller black holes. This graphic highlights the mechanical flaw in that theory. When two black holes collide, their random opposing spin directions average out. The spins essentially cancel each other out. Because of this averaging effect, the new daughter black hole that emerges from a merger is almost always sluggish and slow spinning. But the black holes recorded by LIGO were spinning at nearly the speed of light. That extreme level of rotation makes it mathematically impossible for them to be the product of multiple random mergers. The addition of magnetic fields perfectly resolved the anomaly. It provided the exact cosmic forge necessary to create both the impossible mass and the extreme speed recorded by LIGO. This simulation points to a direct relationship between a dying star's magnetic strength and the black hole it leaves behind. Strong magnetic fields rip away matter and slow things down, while weaker fields allow for heavier, exceptionally fast-spinning remnants. This suggests the mass gap serves as a populated hiding spot for intermediate giants that were previously invisible to our detectors. Astronomers are already planning to verify this in the wild. The powerful magnetic explosions modeled in the simulation should generate highly luminous, short-lived gamma-ray bursts. By hunting for those specific light signatures with next-generation telescopes, we can confirm the birth of these massive objects in real time. For nearly a decade, we stared into the dark, assuming an entire class of celestial bodies couldn't exist, simply because our math was incomplete. Every time an anomaly contradicts our models, it forces us to refine our physics, aligning our theories with the actual behavior of the universe. The mystery stalled until a team at the Flatiron Institute, led by Ori Gottlieb, accounted for a variable long omitted from stellar collapse models: magnetic fields. They built a new simulation starting with a 250 solar mass star and introduced heavy magnetic fields into the swirling disk of stellar dust that surrounds the newly born black hole. As the disk accretes, the magnetic fields twist up tight, exerting extreme pressure on the debris. This triggers violent relativistic jets that blast huge amounts of stellar material entirely away from the core. This chart shows exactly what that does to the black hole's mass. By blasting away half of the star's original debris, the newly forming black hole is starved of material, dropping its final weight perfectly down into the forbidden mass gap. And as the chart shifts to show spin velocity, we see the second effect. Each magnetic explosion provides a natal kick, a sudden jolt of momentum that causes the black hole's rotation to aggressively spike toward the speed of light. By factoring in magnetic fields, the simulation produced a massive, incredibly fast-spinning black hole that sits right in the mass gap. It solved both problems simultaneously. The mass gap isn't a void. Our understanding of how stars transition into black holes was simply incomplete. This work establishes a direct, measurable connection between a black hole's mass and how fast it spins. Stronger fields create lighter, slower black holes, while weaker fields yield heavier, faster ones. This means the cosmos is likely filled with a vast, hidden population of these massive, fast-spinning phantom black holes, waiting out in the darkness. To find them, astronomers know exactly what to look for next. The magnetic explosions that create these massive objects should generate specific, highly energetic gamma-ray bursts that we can spot from Earth. A signal lasting 1/10 of a second revealed a mechanism for creation we previously couldn't explain. Now we know exactly what to look for to find these phantoms in the dark.